So let's start for today. What we are doing today is we progress through our discussion on operating systems and hopefully, um, we finish the operating system part today. We are in the middle of file systems, so we are a little bit behind schedule, a little bit more behind schedule. So we will skip some parts of processes and threads, but still there are some concepts in processes and threads that I want to discuss with you today. And the goal is for next time to start with network structures then. So without further ado, let's talk about file systems. And last time we introduced file systems, we talked about the topic from the user's perspective. We saw some storage media, um, especially hard disk drive, HDDs, and solid state disks, SSDs, and we took a look at their physical operations, where an HDD has mechanical parts in it. So it's basically a spinning platter where bits and bytes are encoded in the form of magnetic fields in memory cells. And in SSDs, we had these NAND flash structures where we used a electron trap in order to encode bits and bytes in an SSD. Regarding tasks, we did, where am I here? We did load program. So we calculated the time it requires to load this program that we have in the table here with 8 blocks and these disk addresses into an HDD. And it took, if you remember, a little bit more than 27 seconds. So we had these 8 blocks with these 3 disk addresses, and these disk addresses were scattered over the storage medium, and you see it in the cylinder value here that we have 3 different values. So the read-read head of the HDD needed readjustments 3 times, and this was like the lion's share of the total transfer time that we calculated. So if you remember, we had this calculation where we calculated the time that we require to read a block and the time that we require for latency. And latency in hard drives is readjusting the read-read head, and this is the sum of the rotational delay and the seek delay in some 9 milliseconds. Questions that were open. You cannot see it. Why can't you see it? Why is there such a delay? Da, 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 da. Hmm. Apparently, so this happened the last time as well. Apparently, there is a bug in my iPad to operating system transfer program. Yeah, anyhow. So my iPad doesn't work again. But still, we can discuss the HDDs. So HDD also has 3 times the latency in it. But as opposed to HDDs, in an SSD, there is no mechanical component. So instead of 9 milliseconds, we have 80 microseconds as latency, because this is the time the SSD controller requires to select the correct chip and perform the electric circuitry that we discussed the last time. So instead of 9 milliseconds, we have a latency of 80 microseconds, and we have a largely improved data rate. So instead of 130 megabytes per second, we have 7,000 megabytes per second. And I want to show you the math real quick. So let me open up one. Yeah, this works. So for HDDs, we had the calculation that we have 3. My setup is not working properly today, so I cannot zoom in. I can zoom in via mouse. Okay, perfect. To enlarge this, so we had 9 milliseconds delay. We need to add 3 times the 9 milliseconds latency into our calculation, and 3 times 9 is 27. So the lion's share of the total transfer time is the latency that we require here. And for SSDs, we have the 80 microseconds here. And now you see the total time it requires to load the program using an SSD is around 250, let's say, microseconds, because the time we require to transfer a block is 0.5714 microseconds. If you put in the numbers, you multiply this by 8 because we have 8 blocks. Then we sum all this up, and we come to the result of 250 microseconds. And now, I mean, 3 times 80 microseconds, it's still the lion's share. So latency is still a thing when we have these small programs, but the latency or the impact of latency is lower the larger the amount of data that you read from a storage drive is. So if you read just 8 blocks from the disk, this is a very, very small file. But if you load a large file, a video, for example, which is in the range of multiple hundreds of megabytes and gigabytes, then the impact or the share of the latency compared to the time that you need to transfer this data is lower. But still, we have 27 milliseconds here, 250 microseconds with SSDs. If you compare the factor between them, it's around 110. In this special case, it's 112, and a factor of 112 is more than significant. It's like game changing, switching from an HDD to an SSD when reading small files. So this was one of the like core insights that we discussed the last time. And if I'm not mistaken, we talked a little bit. Did my slideshow also? Is my keyboard not working? Is this the? Oh boy, actually my keyboard. Oh yeah. Oh. Let me just check if my keyboard is working. It tries to connect. Let me just plug in a cable. The cable long enough? Yeah. Switch it to cable mode. Apparently, something severe crash on my system. Can I click the slideshow? Clicking the slideshow is not fun. Yeah, but clicking the slideshow works. My keyboard is not working. That's hilarious. Yeah, let me click the first part, because then we do a task, and in the meantime I will reboot my system and see if I get my keyboard working, because without the keyboard I cannot operate my system there. But still, we talked about the file system implementation. We talked about logical block addressing. We talked about the main components of a file system being the boot sector, where the information lies to boot the system. And now a light is going off. What's wrong with all this now? Yeah, but you can still see me. But you know, just the light went out. Then we had the super block here. The super block is where the metadata resides. So all the configuration parameters, for example, how big a disk block is. This is in the super block, where the free space management resources reside on the file system, where the inode starts and such. All this kind of metadata is in the super block. Then free space management. It sounds trivial, but it in fact is not. Free space management is one of the core tasks of a file system, so a system to track and manage unallocated space. And then obviously we want to store data in directories, so we organize our information in the form of files and directories. And an index to files and directories are the inodes. So similar as you open a book, if you want to find a particular information in the book, the first thing that you do is you take a look at the index, which is the first couple of pages, the table of contents. It's the index of a book, the first couple of pages, where you have like a pointer to the chapter or the section where your information is located, and then you can jump directly to this chapter/section in order to find your information that you seek efficiently. And the same approach applies for file systems as well. There's an index on all files and directories on the file system. This index is organized according to inodes, and the inodes are a special structure in the file system. The start of the inode is in the superblock, and the inodes are basically the index, the table of contents of the files and directory, which is with the root file, the root directory of the file system, which is the last part of our theoretical file system that we see here. And then, if I'm not mistaken, we talked a little bit on free space management. Unfortunately, I did not make notes when I stopped the last time, so I don't remember exactly, but it was around free space management. If we did free space management, please let me know, because then we can skip this part and save some time. Yeah, but otherwise, there are two methods with which you can do free space management. A little bit suspicious. You still can see and hear me, right?
Yes, everything's okay.
Because everything is like shutting down around me. You can still see and hear me. Okay, perfect. Then let's talk about free space management. We have two approaches there, linked lists and bitmaps. Linked lists are interesting to discuss because this is where file systems started, and bitmaps are the way how file systems do it today. So today in industry, bitmaps are the relevant structure for free space management, but still linked list is an interesting concept because it's a chain of disk blocks where each disk block contains the address numbers of the disk addresses that are free. We have an example. Here. So the diagram that you see, we have three columns in there, right? So this is the first column, then this is the second column, this is the third column. And these columns are disk blocks, which are limited in size. One disk block is typically 4 kilobytes of size. And the general recommendation is not to change the block size of a disk. So typically this is 4 kilobytes in size. So you can host a list, a set of numbers within these 4 kilobytes. And this is illustrated in one of these columns here. This would be then the first disk address that is free, which is 62, then 97 is free, and so on and so forth. But especially when a disk is empty, the linked list that holds all the free blocks is almost full. So when the disk is empty, every block on the disk, except for the super block and the inodes and such, are empty. So this linked list is pretty long and may not fit into a 4 kilobyte block. In that case, we extend the link by another chain. And this is what's happening with the last entry that's in the blue box here, 516. This is not a free block. This is a pointer to the next block, the next chain in our linked list that contains free block addresses. So 512 is not a free block. It's a reference to the next block continuing the list. So the second column is in fact block number 516. And the next free disk block would be 230, then 342, and so on and so forth. Again, 482 is not a free block. It's a reference to the next chain of our link. So the next free block would be 86 because it's the first element of our third chain in our linked list, which is block 482. If there is no reference to a next chain in the link, then we know we reached the end of a linked list, and then the list is complete. So this is how linked lists are constructed. They are quite comprehensive when the disk is empty. They are close to empty when the disk is full. And if you need a new block, so the operating system, for example, wants to write a new file to the file system, it just takes the empty blocks starting from the front of the list. And if a block is no longer occupied, the operating system puts back the address numbers of the respective disk blocks into the free block list. This has some drawbacks. I mean, there are reasons why it is not employed today. Efficiency. So traversing the list may take a long time, especially on large disks. And there you might wonder why. Well, why do we need to traverse the list? We just take the blocks from the front. Well, yes, you could do this, but there is a very severe drawback if you just take the front of the list. Well, if you just need one block of space, then this is fine. But sometimes you want to store larger files, and we also know from the load program example before that it makes indeed sense that the operating system allocates blocks in a sequential range. So if we allocate 62, it makes sense to look out for the next block that is as close to 62 as possible in order to avoid readjustment of HDDs in case of a hard drive. And this is what operating systems do. They try to find consecutive memory segments spanning over multiple blocks. So in the ideal case, if we allocate block 62, we search in the list for blocks 63, 64, 65, and so on. So we, in fact, need to traverse the list, and this is inefficient because you start at the front and then, like turning over pages in a book, you search for blocks that are in the proximity of the first block that you allocate, and this is inefficient. In addition, there's an overhead because each block in the list requires space for the next block pointer. It's not much, but it's still an overhead. Like this blue box here, this requires space, obviously. So the pointer for the next block, so the next chain in our list, and this is an overhead. And we have fragmentation. So oftentimes we do not find a contiguous block fast enough. So we allocate non-contiguous blocks, and this leads to fragmentation. Fragmentation leads to adjusting the read-write head. So instead of linked list, what we do is we use a bitmap. You see a bitmap here on the slide, where one block corresponds to one bit in the bitmap, and the position of the bit in the bitmap is the address of the block it describes. So, for example, block 1. If there's a 1 in the bitmap in the first position, then it's occupied. Otherwise, it's free. So in this bitmap, block 1 is free, block 1 is occupied, block 2 is free, 3 is occupied, 4 is free, 4 is free, 4, 5 are occupied, 6, 7 are free, 8 is occupied, and so on and so forth. So every block has a bit in the bitmap. So n blocks require n bits. The position of the bit corresponds to the address of the block it describes. We search in this bitmap using first fit. If we just want to have one block, then it's easy. But we can also search for contiguous blocks, also according to first fit. This is the way how we allocate blocks. If we release blocks, we just flip the bits, and this has advantages because if we group the bitmap into like 64 bit groups, so 8-byte groups, we have our 8-byte alignment here. So this is like also important here. If we do that, we can do integer operations on that. Because 64 bits represent one integer value in programming. So if you write, for example, int I equals 1, then the Java process will request 64 bits from the operating system because integers are expressed in 64 bits in 64-bit machines. So we can interpret groups of 64 bits as integers and then do integer operations on them. And this is way faster because we can just do the integer operation equals 1. So do a Boolean operation on them, like and 1 or and 1, for example. And this way, perform an operation on the group instead of like one bit separate. So if we want to check if a group is all ones, we just do a logical AND operation on the integer representation of the 64 bits instead of checking each of these 64 bits separately. And this is a speed up. And this technique is called word operation, word being like the size of a register, which is 64-bit on 64-bit machines. And in general, 64 bits are also called a word. 4 bits are called a nibble, 8 bits are called a byte, 16 bits are called a quarter byte, quarter word. A half word is 32 bytes, and a word is 64 bytes on 64-bit machines. And with this trick to interpret sections of the bitmap as larger integers, we can identify some patterns in the bitmap, and this is a speed up. And next we do a bitmap assignment. So let me, or hopefully I don't need the keyboard to log on now. Yes, I don't need it. That's good. Okay, next let's do this bitmap task. Oh, it's declared as homework. Let's do this right now. So it describes a scenario where we have a bitmap that is initially how many bits out there. There is a bit missing, and I cannot change it because my keyboard is not working. But anyhow, at the beginning of a bitmap, it looks like this. First block is occupied for the root directory in this scenario. The rest is free. Then rewrite file A, which uses 6 blocks. Then the bitmap looks like this, because of the first one is occupied, and then according to first fit, we allocate 6 blocks after. So the first 3 are here, the second 3 are here. So in total 6 blocks for file number A. So the bitmap looks like this. And your task now is to perform further actions on the bitmap. So write file B using 5 blocks, delete file A with the 6 blocks, write file C using 8 blocks, delete file B, and so on and so forth. We do this in breakout rooms such that you can discuss. How many breakout rooms do we need? So you have 15 minutes time. 15 minutes is a little bit much. Let's say you have 10 minutes time and the rooms are open right now. Please join the room and work on this assignment. Okay, so in the meantime, I could fix my lighting. So this is working again. I could fix my keyboard. This is working again. And now I'm trying my digital whiteboard if this works. I guess I fixed it again. Basically, I restarted it. But you should see like the, how many bits are these? These are 16 bits. Yeah, 16 bits. And we have file A in this range. So this range, the 6 bits after the first bit, this is file A. And next we want to add file B. B is 5 blocks. So what we do, we allocate the 5 blocks according to first fit. And the 5 blocks are then these 1, 1, 1, 1, 1, 1, 1. The next 5 blocks we use for file B. So 1, 2, 3, 4, 5. And then we have 4 zeros at the end. So file B is actually the last bit of the second nibble and spans over here. So this is where file 2 lies in. Then we delete file 1. File 1 meaning we just flip the bits of file 1. Oh, wait a second. Now, complete. Yeah. Now we deleted file A. The next is we want to add file C with 8 blocks. Well, we don't have 8 consecutive blocks available in our bitmap, so we do the best we can. We allocate the 6 blocks that were freed by deleting file A, and then we allocate the rest. So we allocate this, where file C are 6 bits here and 2 bits there, because the remaining 5 ones in the middle are allocated for file B. There's a last task, I guess. Yes, file B, we delete file B again. So file B meaning that we have 6 bytes there, then we delete the 5 bytes of B, and the end result is like this. Okay. Any questions on bitmaps? Then we proceed with our inodes. So what we conclude free space management. We do it in bitmaps, and we train bitmaps. What we do next is we take a look at inodes. So implementing files. And for implementing files, we need an index. Index is realized using the inodes. It's a data structure where we have the disk addresses of the contents of a file. So basically, you see an inode illustrated here. An inode always begins with the attributes. An attribute can be like the name of a file, the total size of the file, the permissions of the file. So if you remember, a file has read, write, execute permissions, the owner of a file, the group of a file. All these kind of metadata describing files are listed in the top of an inode. This is the attribute section at the top. And then following the attributes are the addresses of the contents of the file. So typically one inode holds 16 addresses, 16 block addresses, which are called the direct addresses here. And if a file is bigger than the 16 blocks that fit into one inode, we can extend the direct addresses by the indirect addresses. And we use the same concept as we have seen for linked lists. So we have an address of block pointers, which points to the next disk block containing additional disk addresses to complete the list of all block addresses of a file. And this is an inode. Basically, three parts. We have the attributes, we have the list of the disk blocks, and we have the pointers to, like, when we want to extend the list of disk blocks. And this is it. This is an inode. This is how we implement files. Interesting are also how we implement directories, because technically a directory is a file. And if a directory is a file, a directory is also implemented using an inode. So every directory is indexed using an inode, and instead of having the contents of a file in the list of disk blocks, what an inode of a directory contains is the list of directories and subdirectories, and also files that are included. And each entry in the list of subdirectories and files contains a pointer to the inode where the respective directory lies. So for example, here in this diagram, you see the architecture of an inode of the root directory. It always starts with the attributes. And in the root directory, we have the subdirectory user, we have the subdirectory lib, and we have the subdirectory temp. And we can also have like files. For example, the swap file is a plain file that lies directly on the root directory. And this list is contained in the disk block content of the inode of the respective directory. And each entry in the list contains the name, obviously, so the name of the directory or the name of the file, but also has the information where to find the inode of that directory or of that file. And this is illustrated here. What you see here, the 6,378, this is not a block address, this is an inode number, because the inodes are also like indexed using an integer. So we start with inode 1 and inode 2 and then inode 3 and so on. So these are inode numbers, meaning that the inode that has all the informations about the user directory is found in the inode located at number 6,378. And the same for files. So if you want to have the content of the swap file, you take a look at inode 2693, and there you find the disk block addresses of the respective files. So for implementing files and directories, we use inodes, and this is quite simple. It contains the attributes. In the case of files, it contains the block addresses of the content of the file. In case of a directory, the content is not the content of the directory, or the content of the directory is a list of subdirectories plus files that are contained in the respective directory. And the attributes are the file name, type, permissions, owner, group, and everything. So what does the operating system do when accessing a file by its path? This is described by this pseudocode algorithm here. So given a path, how does the operating system find the contents of this file described by the path? And this works as follows. We always start with an inode of the root directory. So we introduce a variable, current inode, and we set this value of our variable inode to the inode number of the root directory. This is known, typically the inode number of the root directory is 2 by definition. But this is part of the superblock. So the superblock knows the inode number of the root directory. Typically, this is 2. So we start with the root directory, and then we split up the path by this delimiter // So maybe I can show this to you on the whiteboard. So if you have, for example, a path /home /Wölfe /exem questions.pdf, right? So if you have a path in a string such as this, if you apply the split method on it, split with the delimiter / on this, what the split method does is it splits according to /, and the result is an array of the components. So the first element would then be home. Then we would have our Wölfe. Then we would have exam. And then we would have questions.pdf. So the split method takes a delimiter value and splits a string up into an array. And the array elements are like the components resulting of the splitting up. This is how the split operation works. Here, this one. So if we have a for loop over this array that results from the split operation, we iterate over the parts of the path that we are inputting it as input parameter. So for part in this array, we find in the current inode the part. So for example, or in our example, the first part would be home. So in the current inode that is initialized using the root inode, so in the root directory, we search for the inode for the directory home. We find this in the root directory because the root directory contains the home directory. And what we get back is the inode of the home directory. Then we go into the next loop iteration. Then we have our Wölfe. So we search for the subdirectory our Wölfe in the directory home. Get the inode for that. Then we do the same with the directory exam. And then finally, we go into the last iteration of this for loop. Then what did we have? Exam PDF. So we search in exam PDF of the subdirectory exam, of the subdirectory Wölfe, of the subdirectory home, which is a subdirectory of the root directory. Basically, we traverse the path starting from the root directory and taking a look or searching the inode number for the next step. So starting from the root directory, we search for the inode number for home. in the home directory, we search for the inode number of our Wölfel, and so on and so forth. So at the end of this loop, we have the inode of our file that we want to read in current inode, and then we can read the blocks. Because in an inode of a file, we have the block addresses after the attributes there. And then the result is given back to the operating system. Okay, any questions so far? Then let's talk about a technique that's called journaling, because this is a feature that allows modern file systems to be resilient towards crashes. So if you remember the last time we said, well, file systems have two purposes. They need to access files fast, and they need to be fault tolerant in a sense that if the file system crash or the storage medium crashes, the files should be consistent in a sense that the information that we store in a file should not be corrupted by any means. And journaling is the way how we can achieve that. Journaling means that we maintain a journal, like a journal where you write up things on a day-to-day basis, basically a diary, so to say. And this works that we write into the journal what we are doing next before we actually do it. So if we delete a file, for example, a lot of things need to happen, right? So we need to when we delete a file, we need to remove the inode of the file from the inode structure. Then we need to maintain the free space management and flip the bitmap. This needs to be done when we delete a file. And then obviously we need to delete the file from like the files and directory part, right? So many steps are required to delete a file, for example. And if the system crashes right in between, so for example, if we manage to update the inodes and remove the inode entry for the file we want to delete, but the system crashes before we update the bitmap for free space management, then we have a problem, because the file is gone from the index, but the bits for the blocks where the file have been are still 1 and out of scope for free space management then. This is a problem. So what we do is we write up what we want to do. So like in the journal, we write up, first we want to, first we do the maintenance on the inode structure, then we update the free space management, and then we actually remove the file. We write that up, and then we perform the actions. Because when a crash happens during writing up, it's not an issue, right? Because the file system is still intact. If a crash occurs while performing the steps of deleting a file, we have a log of the changes that we wanted to do, and this makes it easy to recover from it. So recovering either by continuing the operation or by undoing the operation. So if in our example, we want to delete a file and the file system crashes during updating the bitmap, then the operating system starts after the crash and takes a look at the log. And if there is an entry in the log, like we want to delete a file, and you see, well, the file is gone from the inode structures, but the file is still in free space management, then the operating system can then continue on the point where the crash occurred. And if it's successful, well, the log entry is removed. And in case of a crash, the log checks for this pending operations. So we can rerun it until it's completed. and this simplifies the recovery. Basically, any file systems that we use today use journaling. So the Linux file system X4 uses journaling, NTFS on Windows uses journaling, and the Apple file system uses journaling as well. The last technique slash issue that we address is fragmentation, but we talked about fragmentation already. So we can make this quick. Well, fragmentation is a condition where data is stored in a non-continuous way. For HDDs, this is like poison because we need to readjust the read-write head all the time, and this increases latency times. SSDs are unaffected in a sense that SSDs still have a latency. And so it makes a difference if we read like randomly on an SSD or if we read a consecutive segment from an SSD. So the latency is way lower than for HDDs, but still it's not gone. Yeah, file systems are designed to mitigate these fragmentation issues to optimize performance. One way to do so is moving from a linked list free space management to a bitmap free space management, where it's way faster to search for consecutive segments in a bitmap. In illustration, this is a fragmented disk on the left-hand side, defragmented disk on the right-hand side, and you see easily, well, you need to adjust the read-write head on an HDD once. You can read the whole file and then be good with it. Whereas at the fragmented disk, you need to adjust the read-write head to point to the correct cylinder. Let's do a quick assignment before we complete file systems. So there is an assignment, continuous allocation. Let's see what this is about. So let's take a look. Yeah, well, basically we did these calculations already. We could, for the sake of being faster through file systems, skip this task because it's basically the same as we did for load program. So in load program, we calculated the time that we need to read and write files. File relocation is an extension to this type of file where you say, well, how long does it take to relocate a file? But this is basically just twice the time in order to access the file. So we can, let's skip file relocation and disk compaction. You can do this as an exercise for the exam at home. And if you have any questions, please let me know. But one thing that I want to mention is the types of fragmentation. Before I address the question in chat, the types of fragmentation, which we can see here as well. So in memory management, we talked about external fragmentation and internal fragmentation, and you see these two fragmentation types as well if you take a look at this picture. So internal fragmentation would be what happens at file 3, for example, where you allocate space in certain chunks, like a disk block, or in 8-byte alignment, as in the example of memory management. And if you just, for example, require 2 bytes out of these 2 kilobytes out of these 4 kilobytes that you get from allocating a disk block, then this is called internal fragmentation. In external fragmentation, you can see the gaps between file 1 and file 2 and file 2 and file 3 respectively. This is external fragmentation. Yeah. And what you can do is you can close the gaps. This is called defragmentation or file relocation. So you can move file 2 to the left by 2 blocks in order to close this gap here. And you can do the same with file 3. So you move it by 1 block to the left in order to close this gap. You can do this, but this takes a pretty long time. And the task here is to calculate how long it would take to compact half a 2 terabyte disk. And spoiler alert, it takes a very long time. So it's I guess it's 67 hours in order to compact or to defragment 1 terabyte out of a 2 terabyte drive. But then, well, you mitigate external fragmentation. So, a question from Jeff Bezos. Well, whatever task we skip will not come in the exam. Well, I mean, we did this kind of task in load program. So in load program, we did calculations of how long does it take given the seek time and the rotational delay. The same type of question is continuous allocation as well. So if I say we skip this continuous allocation task, this does not mean that you don't need to have, like, you don't need to calculate something in the exam. So the answer is, well, if we don't skip question types, but also this is not a guarantee for the exam. So anything can happen on the exam. And if we do not do a task, this does not mean that this is then out of scope. Basically anything that we discuss is in scope of the exam, except it's explicitly declared as optional, or it is explicitly declared as excursus. For example, there is an excursus on the ext4 file system that we will not discuss because of time reasons. And this case study is out of scope. It's not declared as excursus, but this will be excluded from the exam. I will maintain a list on what is excluded from the exam, and I will publish this list then on iLearn at least 2 weeks before exam time. Okay. So for the interested reader, there is a case study on how exactly the ext4 file system on Linux works, because they have some techniques employed there. You can read it at home then. So let's sum it up. So this is the file system section. What competencies should you have acquired? Well, you should be able to define and explain the newly introduced technical terms, method, and technologies, the same as always. You should be able to describe the difference between a hard and a soft link. We did briefly talk about hard and soft links. You should explain the procedure reading from a file using system calls. We did this the last time. You should be able to format and mount disks in a Linux distribution. You should describe SSDs and HDDs, the technical structure, recite the data access procedure, compare SSDs and HDDs this way, and given the parameters of the disk, calculate the loading time of the program, explain the concept of logical block addressing. Then what we did today, name and describe the main contents of the file system. So what is a superblock? What is a boot sector? What is free space management? What are the inodes and such? Then discuss and explain free space management using linked list and bitmaps. Illustrate the bitmap by example. Recite the approach on implementing files and directories using inodes. Explain the procedure to access a file by its path. This was the small algorithm that I showed you a couple of minutes before. Then we talked about the Schornerling file systems, and we cross out the last one, given a suitable scenario, calculate these compaction times. Because theoretically, you should be able to do so by by passing this point. So if you know the loading times of a program, then you can also calculate completion times. For the sake to make things easier, let's cross out this one. Are there any questions? No. Then let me load up the next slide deck, which is processes and threads. We will skip a major part of processes and threads. We will skip threads. We will talk about processes only. And to start with processes, we clarify the term the process model. So the process model basically describes the state transitions a process goes through in its life cycle. So there are several states for a process. A process can be new when it's newly created. A process can be ready when the process is loaded from the disk into memory, but it has not executed a single instruction. Then it's ready, loaded but not executed. Then it's running when the process is assigned a CPU and is executing. A process can be blocked as well. So for example, when the process is waiting for a keyboard input or the process is waiting for a sheet to be printed out. So basically input-output events that occur. And then a process can be terminated, meaning that it has been completed either successfully or unsuccessfully. And a process that has been terminated unsuccessfully is known as a killed process. So the correct technical term for an involuntarily terminated process is actually the process has been killed. The state transitions are shown here. So whenever a process is initiated, so if you double click on a shortcut on the desktop, for example, then the process starts anew and then the loading phase begins. So all the instructions are loaded from disk into memory until the process is ready. When the process is ready, the process needs to wait for the operating system such that the operating system assigns a CPU to the process. And nowadays we have multi-core, multi-process processor or multi-CPU systems. So the operating system assigns the hundreds of processes in the system. Did I show you how many processes there are in a system? If not, I will do it right now. Oh, I have to configure this. Yeah. So you should see my shell. The ps command is used to show all the processes that are currently running. And if you add the option AUX, you get a list of all processes of all users that are currently in execution on the system. And it's quite a lot. In order to count these, we can use WC-L. And there you see that currently, or you don't see, that currently 525 processes are running on my system. But we do not have 525 CPUs in our system, meaning that processes are interrupted when they are running. So the operating system takes away the CPU from a process and then it goes back to the ready state again. So the term for the operating system assigning a process to a CPU to a process is this dispatching arrow here. And then the process transitions from ready to running. If the operating system then takes away the CPU, the process is interrupted and it goes to the ready state again. And this happens all the time. This is called a context switch, where the CPU is assigned to another process. And also processes can be blocked. So from running, they can be blocked. And blocking means that the process waits for I/O or an event to be completed. If so, the state goes to ready. And from the running state, we can go to terminated. Events that can cause processes to be created are system initialization. So if you hit the power button and the system boots up, the first process is created in the system, which is the operating system kernel. Then system calls can create child processes. So one process can create another process. This is possible. And processes can be invoked from other processes, like user requests. When you enter something in a shell command, the user does. Technically, this is then a system call of the bash shell. So the bash shell invokes the operating system by a system call, creates a child process, and so on. And yeah, the command you can that we have seen before, it's the command to list all running processes. So these are the events that can create processes. Note that if you terminate a parent process, all child processes are terminated as well. In this example, if you terminate A, for example, then all the processes are gone. So if you crash the operating system, you cannot use your computer anymore. But also, if you create a process from a shell and you terminate the shell, then the process that you create from the shell is also terminated. You can terminate processes voluntarily. Then the exit code is 0. So every process has an integer value when it terminates. If this integer value, which is called the exit code, is 0, then the user knows then that everything is fine. The process terminated voluntarily. You can also, or voluntarily and successful, when the exit code is 0. A process can exit voluntarily, but with a non-zero exit code. This is possible. Exit codes, by the way, are in the range of 1 to 255. So, for example, or I use the virtual machine because you can do this with your virtual machine. Well, remind me later for update. Updates are important, but let me remind later. So, my shell here. If I do an ls/temp, right? So you get the contents of the temp directory. But you see here where my mouse is, there is no number left to the shell prompt. Now, if I do ls/temp2 and temp2 does not exist, why does it not show the number? Does my shell show the number? So let's do it on my shell. /temp, it's fine, yeah, right? So I need to move my head. Now you see the whole shell. If I do ls/temp2, yes, you see the number there. So on my shell, I'm using a set shell. I'm not using a bash shell. So bash shell apparently does not display exit codes, but the set shell that I'm using does display the exit code. And this is the case where a process terminated voluntarily. So I did not kill it, but it terminated in an error state because you see the error message here. So this would be the second bullet there. Then we can exit or terminate processes involuntarily. So in case of a fatal error, exit code is non-zero. And a process can be killed by another process. So the operating system can process another process with an exit code that is static 137. but also involuntarily. There is a command to do so. I will briefly show you the command. It's the kill command. If you have a process and with PS or AUX, you can list all the processes. Let's grep for bash to see our grep for bash to see. Well, this is the process in PSAUX that corresponds to the bash shell, so the window that I'm just wiggling. And if I write kill bash, then this does nothing. What you can do is this is pretty famous in bash scripting. If you do a kill -9 and then you take this number, this is the process ID, then this should kill my bash shell, and it does. So I crashed my bash shell basically. So one process, so the process that I spawned on the bash shell killed another process, exit code 137. Let's do another assignment before we go into the break. There is a somehow fun assignment, the fork bomb, that you can try out. So let's see. Oh, I guess I need to change this a little bit because I know that there are white spaces missing. How it works. So what I want you to do is to open up your terminal of your Ubuntu virtual machine, run two terminals. The htop terminal where you execute htop, so to monitor the system resources. And in the second terminal, you enter this sequence that is shown here. And then you observe what is happening. So please do so. Everyone can do this on its own. Yeah, 10 minutes should suffice to do so. Then we do a break, and then we discuss the fork bomb and talk about scheduling. Okay. Is there any question before we go into the task assignment? That's a no. Then we talk to each other again in 25 minutes. Well, welcome back, everybody. Let's talk about the fork bomb. I mean, the name indicates already what is happening here. Yeah, let's make this one bigger. Let's make that one bigger. So what you see here on my virtual machine is my system resource monitor with HTOP. And you see I have 4 cores allocated to this virtual machine as well as 2 gigabytes of RAM. Actually, I should have allocated less cores, but still, let's see what's happening. And then I put the sequence that you find in ilearn into a shell. And if I execute it, then at first nothing happens, and then I get these weird error messages. And yeah, unfortunately, my my virtual machine is unresponsive again. Huh. So what's happening here? So this terminal is not responding, and you see, yeah, well, the load in the second HTOP window is pretty much, and the pressure on the main memory is also pretty high. So let me kill this shell, and then you immediately see the effect that I was talking about before. So if you kill the process that spawns another process, then all the children processes are killed as well. So what happens in this fork bomb? So what happens exactly when you type in this sequence? Well, let me just copy it and then put it into a, I guess I have already forkbomb.sh. Let me create a new file. So bigger a little bit. So what actually this sequence constitutes is the following. So there's a mention in chat, displays are not clear. What do you mean are not clear? Can you see it? Is it like not sharp enough? Because from my OBS studio, I see it should be transmitted fine. I don't know. Okay. So better to make it a little bit bigger in order to to counter the fuzziness and unsharpiness. And if I write this this sequence of characters into an editor, you get the syntax highlighting, and there you see as well that the first 3 characters are basically highlighted, and the type and the ampersand are also highlighted as well. So what this sequence basically constitutes, this is a shell function, right? So if you add some line breaks, then you see, well, what this fork bomb actually is, it's a shell function that is named colon. I can just change the name here, right? So if I change it to bomb, add some more white spaces, the functioning of the sequence should be clear now. So what this does is, I have a function that's called bomb, and what's happening inside the function is that I execute bomb. So I invoke the function from the function. So this is a recursive function. I don't know if you talked about recursive functions or recursive methods in programming 1, but if not, a recursive function or a recursive method is a function or method that calls itself. So basically what's happening here. So inside the body bomb, I invoke bomb, but there's more. I invoke bomb and pipe the outputs of bomb into another process that executes the function bomb. And what this ampersand sign does is it moves the line into the background. It starts two processes and creates a connection between these two BOM processes such that the output of the first BOM process is the input of the second BOM process, and then we move this into the background. And as this is a recursive function, it calls itself. And this way creates an exponential invocation of the same process all over again. This is what's happening here. The semicolon, it's a separator of commands. So if you just have a line and you want to have two commands in the line, so for example, the ls command and the date command in the same line, you can separate these two commands with a colon. If you have line breaks, you actually don't need the colon, but in our example before here, we separate the invocation of the function by the definition of the function by this colon here. So this is how fork bombs work. You spawn processes all over again until your system or your shell eventually crashes. Any questions? Web 13. Close this. And let's move forward with the last chapter that we talk on processes and threads. So see, we are at section 4 now of this chapter. So we skipped section 2 and section 3. So we skipped threads and we skipped thread synchronization. This will be out of scope for this term. So we pick it up again with scheduling. And we briefly talked about scheduling before. So scheduling is the process that the operating system does to assign a CPU to a process. Scheduling in general, or it can be generalized to any resources, but typically in an operating system, this is CPU time or CPU time slices, because the operating system can also decide to take away the CPU from a process. In terms of terminology, the scheduler is the part that's responsible for scheduling, and the scheduling algorithm is the strategy or method the operating system uses in order to make the scheduling decision, like which CPU is assigned to which process. Because if we do this smart, we can increase both performance and the user experience. If we don't use it smart, then, well, we don't have the benefits of more performance and user experience. But the decision on which process should get which CPU is mainly affected by these two categories of processes. We can have CPU-bound processes and we can have I/O-bound processes. In the slide here at the top, you see a CPU-bound process, where this process A requires the CPU most of its time. So time flows from left to right in this diagram, and process A, if you compare it to process B, you see clearly it has longer CPU bursts. And process B has shorter CPU bursts. And in between CPU bursts, well, the processes are waiting for I/O, for example. On average, to give you like a little bit of a feeling how I/O heavy processes are, on average, processes are waiting 70–80% of their time for I/O. So for example, the slideshow that I'm presenting to you right now, it waits for my input in order to show you to the next slide. And these two types, or these two characteristics, is a process CPU bound or is it I/O bound? This has a big impact on the decision making an operating system does in the assignment CPU to process. Because Processes that are I/O heavy, so they are I/O bound, these are interactive processes. Interactive means they have interaction with a user. And whenever a user is involved, we need to be careful. So let's take a look at scheduling goals for interactive processes. So processes that you actually use, meaning not background processes. So processes that uses interact. Fairness is an issue. Giving each process a fair share of the CPU, no process should be treated specially if there is no special reason for this. Balance. Keeping all components of the system busy, because if we can have a load on every CPU or CPU core that we have, this increases performance obviously. So we want to schedule in a way where we use all the resources that the hardware of the computer gives us. Response times, especially important when working with users. Users are not patient by default, and users have expectations that we need to meet. These expectations are under the goal of proportionality. So users want to have quick responses, and users want their expectations to be met. But users have an inherent but often incorrect idea of how long things should take, and this obviously has an impact on the scheduling of processes in other words, what a scheduling algorithm should take into consideration is that the user has expectations, and if it's possible, we should meet the user's expectations in order to keep the user happy. But for background processes, we have different goals because we don't care about response times or expectation the user has for background processes. So background processes like a backup job, or if we are talking artificial intelligence, like the model training of a complex AI model can be realized using a background job, meaning that it has no interaction with a user. And there we are simply the interest there is throughput, meaning we maximize the number of jobs the machine can perform in a certain amount of time, like jobs per hour, for example. And then we have turnaround time, like minimizing the time between submission and termination. Okay, and given these goals, let's see which basic scheduling algorithms exist and how the Linux kernel combines them in order to come up what we have right now. Because Linux has a very sophisticated scheduling algorithm, and this is current subject of research. So Linux people still do a lot of research on scheduling because it is a performance indicator, and obviously scheduling, if you do it right, you can gain a lot of performance out of smart algorithms there. But we start with what we already know, FCFS, first come, first serve, the scheduling algorithm where processes are executed in order over time. We saw first come, first serve in memory management as well. So where we, based on the time, removed processes from memory, and we can apply the same algorithm in scheduling. It's the most basic scheduling algorithm that we have. And this is not always a bad thing. We saw this with other algorithms as well. We can hardly say an algorithm is better than another algorithm because it always depends on the use case. So first come, first serve may be not the best choice for interactive processes, as we will see, but first come, first serve may be a good candidate for background processes. But let's see how first come, first serve works. Straightforward to implement, and it's a non-preemptive algorithm. Non-preemptive means that once a process is assigned the CPU, the operating system will not take back the CPU and interrupt the process. This would be a preemptive algorithm. So preemptive means that it can be interrupted, and accordingly non-preemptive means that it cannot be interrupted. So once a process is running, it runs until completion. But this can have some negative effects, especially on interactive processes, because it can lead to the convoy effect. So if you drove a German Autobahn, for example, then there are times where you can suffer from the convoy effect. But anyhow, just imagine a road with 2 lanes and 2 very slow vehicles drive next to each other on these 2 lanes. Faster vehicles approaching from the back cannot overtake the 2 slow vehicles because the 2 slow vehicles, they occupy the 2 lanes that we have. And this is like the convoy effect. A fast object cannot overtake a slow object. And this happens if you do first come, first serve in a non-preemptive way. To demonstrate this, this is a running example. Let's take a look at this table here. So we do scheduling on a set of processes. You see the set of processes in this table here. So we have process A, B, C, D, and E. And each of these processes have a burst time and an arrival time. Arrival time means this is like the time unit when this process transitions from new to ready. So when it's loaded into memory and in theory can be transitioned to running. This is the arrival time. And the burst time is the time a process requires the CPU. So process A for completion requires 5 time units to complete the burst time, the amount or the number of time units a process requires to complete. And in first come, first serve, we execute them in order. And if A, B, C, D, E arrive in order 0, 1, 2, 3, 4, then first come, first serve does exactly the scheduling as you see it here. First one, then B, then C, then D, and then E. So what you see below here, this is the schedule for A, B, C, D, given these parameters shown in the table. And we use the same example to discuss more sophisticated algorithms. And the next one that we will talk about is round robin. We talked about round robin as well. So round robin basically means we take turns one after the other in a cyclic manner. But round robin is a little bit more complex when it comes to scheduling. You can use round robin as in scheduling, but this is not as trivial as it sounds, because we have a fixed time slice, or in other words, round robin is preemptive. I have it here. No. Round robin is preemptive, meaning that in round robin scheduling, the CPU can leave a process, so the operating system or the scheduler of the operating system can take away the CPU from a process and interrupt it. So every process in round robin has a fixed time slice of CPU time, and we call this the quantum. And the quantum is fixed. So every process has a fixed quantum. And if the quantum is over, then the process is interrupted. We say the process is preempted. And then the CPU is assigned to the next process. Priority does not play a role. It treats all processes with equal priority, which on the one hand is good in terms of fairness, but experience has shown that this is not always desirable, because you also want to meet the expectations of a user. And if we have a high I/O bound process, meaning the user interacts with this process pretty frequently, in order to meet the expectations of the user, maybe we want the idea of priority in order to have processes in a higher priority than others, for example. And there's this quantum length trade-off, because whenever a process is interrupted and a context switch happens, this takes time because, well, we need to load the register values from the CPU, save it in memory or on disk, and then we need to load the register values from the process that gets the CPU then, and so on and so forth. So this context switch comes with a little bit of computation effort. And if you do more context switches, you obviously have more computation effort. And you have more context switches if the quantum is just a small amount of time. The larger the quantum, the fewer context switches you have, but a long quantum also degrades response times. So this is a trade-off. What do you do? And in Tannenbaum, well, you barely get exact values. What is like a good configuration option there? But Tannenbaum in the book suggests a quantum of around 20 to 50 milliseconds as a balance compromise there. Okay, let's see how round robin works. So the basic idea here is we have processes A, B, C, D. Here we have B, F, D, G. And if B is the current process, B runs as long as the time quantum allows B to run. If the time quantum is up, then B is, or the operating system takes away the CPU from B. B gets at the end of the list of runnable processes. Yeah, so we assume that these 4 processes are able to run. These are the runnable processes. And B gets to the end of the list of runnable processes, and the CPU is assigned to the next one in the list. Basically, we enqueue processes based on their time of arrival, and then if the time quantum is up, the process is then moved, is moved to the back of the list, the end of the list. Then. So we take turns, basically, round robin scheduling. So this is the schedule for round robin. And let's say the quantum size is 2 time units. So let's start with here, time 0. On time 0, process A arrives, and the list of runnable processes is empty. Fine. We start process A. Process A runs or starts to run. On time 1, process B is added to the list of runnable processes. So our list of runnable processes then is A and then B. And A is currently running, right? So this happens at time unit 1. What are we doing on time unit 2? And this is important because in time unit 2, 2 things happen. On the one hand, C arrives. C arrives at time unit 2, so we add C to the list of our runnable processes. I misclicked. C is the list of our runnable processes. We have time 2, not time 1. Time 2, right? So, and the current process that's running is A. But at time 2, 2 things are happening. Process C arrives and process A reaches its time quantum because quantum size is 2. Meaning that at time 2, A finishes the time quantum and goes to the back of the list. So from A, B, then C arrives, we move to B, C, A. And there you might have the question, if two things happen at the same time, what happens first? And the rule is we add newly arriving processes first before we do the context switch. New arrivals first, then the context switch. So we add C first to the list, and then we do the context switch where we execute or we initiate the execution of process B because it's the next in the list, and we add A at the back of the list. So the list of runnable processes after time 2 is B, C, A, and B is executed. So let's see, let's clear this. We have B, C, A. B, C, A. B is currently executing. At time 3, B is coming in, and we do not have a context switch. Fine. So B, C, A, D. Next, we have time 4. In time 4, what happens here? So again, two things are happening. E is coming in. We have B, C, D, E. Then we do the context switch. So C, A, E, E, and then B, and we start executing. This is what's happening on time 4. On time 5, because C has a burst time of 1, so it completes after 1. The list goes from C, A, D, E, B to A, D, E, E. Time 4, because the C, cross it out properly, because C is leaving, and our next in the list would be then A. So A is executing. A has already had two time units, the CPU time, and it runs, you see it here, from 5 to 7, adding 2 more time units that was executed. So on time 7, the time quantum of A is up. So A is interrupted, and according to round robin, we D, E, A, we move it to the back of the list. The next, according to the list, is D. D, then E, then B, then A again, and the last one is then E. So this is round robin schedule. The important thing is what happens if two things happen at the same time. So process arrives and a context switch needs to be performed because the quantum size is up for a process. What happens there? We do first the arrival, then the context. Any questions? Good question. What if there's a gap in arrival times between two processes? If a process can run, then a process will run. If there is no processes that can run and no process is arriving, then there is a gap in execution. Then the CPU would be idle. Okay. The next algorithm is shortest process next. This is an interesting algorithm because shortest process next optimizes towards response times. It works accordingly, according to the name. The process with the shortest remaining burst time is the one that is selected for execution. So if a process runs and a shorter process arrives, the operating system preempts. So shortest process next is a preemptive process. So whenever there is a process that is shorter as the current executing process, the operating system preempts the current executing process and switches to the shorter one. It's minimizing average response times. But shortest process next is interesting in its idea because of the lowest response times, but does not see much application in industry because completion times are challenging to predict. But still, let's do this exercise with shortest process next. So we have our table again. So process IDs A, B, C, D, E, arrival times 0, 1, 2, 3, 4, and we have the burst times S. So at time 0, again, we have process A, and on time 1, here you see it, we have a context switch because the remaining burst time at time 1 of process A is 4 because it executed for a single time unit. So the burst time at time unit 1 for process A is 4. For process B, which just arrived, is 3. 3 is smaller than 4, so we start with executing process B. Context switch happening at time unit 1. Time unit 2, we have a 4 here. We have executed B for a time unit, so we have 2 here. And then at time 2, C arrives. C has a burst time of 1. 1 is smaller than 2 and also smaller than 4. So the shortest process in our list of runnable processes is C. So we do a context switch again. At time 4, so C is out of the system because C only requires the CPU for a single time unit. Is good. At time 3, here, time 3, we have 2, and now we have a the conflict, so to say. We have 3 processes in our list of runnable processes where 2 have the same duration, and there you do it according to the order, like round robin. The first process that came into the system has precedence over the process that came later in the system. So we execute B instead of D in this case. Also, this is like an important information. If you have multiple processes that are the shortest one, you prioritize the processes that are the longest in the queue of runnable process. So we start with B. B runs, before we start with B, this 2D did not execute. Let's talk what happens at time 4 real quick, because at time 4 we have a process with burst time 3. 3 is bigger than 2, so there's no chance that we execute E. But starting from time 4, like on time 5, all the processes that are not crossed out in the table are currently in the list of runnable processes, but at time 4, B executed for another one. So at time 4, B has a burst time of 1. So we have 4, 1, 2, 3. At time 5, B is completed because it finished its 3 time units. Cross this out. So D has 2, E has 3. So after B, according to shortest process next, we execute D. D runs for 2 time units, and we can cross out D. After D, well, we have E and A. E has 3 burst time, A has 4. So we execute E from 7 to 10. And this is out of the list. And then finally, we finish A. Any questions on shortest process next?
Do we also first add the new arrival and then change the priority, the context?
Yes, yes. So whenever a new process arrives, we do the arrival first, such that we do the context switches based on or including the new arrival. Okay, next is priority scheduling. Story so far. Story so far is first come, first serve is not ideal for interactive processes. So round robin would be the next best thing where we have a fixed quantum. This is nice, but it says here, well, sometimes in order to meet user expectations, we want to have priority. User expectations is not always like fast response times, but also fast completion times. And you see it here, the response time. So the first like time unit here of process A is very short. So it's the first process that started, but also the last process that ends. So in order for meeting user expectations, where the user wants both, like an early start and an early end, this is also like suboptimal. Priority scheduling addresses this, where it takes a priority value into the whole consideration. So priority scheduling is basically round robin with a priority value. Each process is assigned a priority, like an integer. Priority with high integer values is or should have precedence over processes that have lower priority. So lower values, lower priority, higher values, higher priority. And we execute higher priority processes before lower priority processes. So processes are categorized based on priority levels. Only processes with higher levels of priority are executed. And if we have multiple processes with the same high or low priority, we do round robin scheduling. So basically, we categorize processes by priority and do round robin inside these levels. If a top priority level is empty, then we shift the execution to the next lower priority level. and do round robin scheduling accordingly. So here you have an illustration of this. Here we have 4 priority levels, 1, 2, 3, 4, whereas 4 is the highest priority and 1 is the lowest priority. And you see the list of runnable processes on the right-hand side here. We have 4 processes in the highest priority. We have 5 processes in the lowest, not lowest, but in priority 1 lower, in priority 3. And we have this poor boy here, which is priority 2. Where we have 1 process. So in terms of execution, this means that at first we execute in a round robin fashion all the processes that have the highest priority. And if there is no process left in priority 4, we switch the execution to priority 3, execute the processes there according to round robin, and do then the same for priority 2. Example. Again, A, B, C, D, E. Again, 0, 1, 2, 3, 4. First times are also the same, but for priority scheduling to work, we need to assign a priority to a process. So we have an additional column with the priority, and we say process A has the highest priority, priority 3. B has priority B, C has priority 1, D2, E also 3. So how does the schedule looks like this, as you see on the slide here? Let's talk about this schedule. So time 0, easy, everything fine. On time 1, we have A and B in our list of runnable processes, but as A has higher priority than B, A continues. Anyhow, yeah, A continues, but this is irrelevant because we do round robin on each schedule level. So we have 2 levels, a level 3 and a level 2. A is the single process on level 3, B is the single process on level 2. And as every level works according to round robin, we also have the concept of a time quantum. Time quantum, if not specified otherwise, is in our example 2. And as A did not finish its time quantum, there is in fact no context switch decision at time 1, but there is a context switch decision at time 2. So at time 2, process A finishes its quantum, and then we do a scheduling decision. And we do the scheduling decision based on the processes that are currently in the list of runnable processes. And here again, new arrivals are added to the list of runnable processes before we do a scheduling decision. So we have at time 2 the decision to make A, B, C, which process do we execute? And we execute process A because process A has the highest priority. So A gets another time quantum. At time 4, we do the next scheduling decision. And at time 4, we do the scheduling decision based on all processes that we have because E arrives at time 4. So here again, new arrivals are added first. Can I see? So this is A is currently executing, and then E. Or this is level 1. On level 2, we have B and D. And on the next lower level, we have C, right? So these are our this is our list of runnable processes according to round robin, not round robin, according to priority scheduling. So we have something in the top priority here, right? So we do the scheduling decision on the top priority. A is currently executing, and then we have E in there. According to round robin, because we treat every level according to round robin, A is moved to the end of the list, meaning that after A finishes the quantum, we execute E for a quantum. Then we finish A because, can I, this work? So we have EA during the time between 4 and 6. At time 6, we do round robin again. So from EA, we go to AE, right? At time 7, A finishes because A has a burst time of 5, completed its 5 time units. So at time 7, A goes out of the picture, but the highest priority still has a process, E. So at time 7, so between 7 and 8, E executes. After or at time 8, E is removed because E finished its 3. So we start executing priority 2 here. There we have B and D. So B runs for a time unit until time unit 10. After time unit 10, E goes to the back of the list. D executes between 10 and 12. At time 12, D finishes the quantum. D goes out of the picture because D, oh no, this is a priority. Because D has a burst time of 2, so it finishes after running for a full time quantum. So B is left at the intermediate priority level until time 13, because at time 13, B finished its 3 time units for executing. At time 13, we finish priority 2. So priority 3, oh, priority 1 of process C. It's the last one that we do, and then the schedule is complete. Oh. This is priority scheduling. Great. Any questions? So these are like how many? We had first come, first serve. We had round robin. We have shortest process first, and we have priority scheduling. So these are the 4 main ideas how we can have an impact on actual scheduling. And what I show you next is what the Linux kernel does, because the Linux kernel combines these aspects into what we call a complete fair scheduler. So this is the name of the scheduling algorithm used in the Linux kernel. So it's CFS, completely fair scheduler, and it works as follows. The Linux scheduler is preemptive. So we can take away the CPU from a process. It's priority based, it's high performant because it's in the Linux kernel, obviously. And so as it's priority based, we have these priority levels. And the higher the priority, the larger the quantum size. Because user expectations, proportionality. We want high priority processes go through the system as fast as possible, and as fast as possible, as performant as possible, means that we shift the trade-off between like completion times and fairness, like towards the performance. So we increase the time quantum in order to get these processes faster out of the system. And then the scheduler maintains two queues. It's an active and an expired queue. These queues are sorted by the process priority, descending, meaning at the front of the list, we have high priority tasks, and at the back of the list, we have low priority tasks. And the scheduling works as follows. If a process is preempted because it reached its time quantum, it joins the expired queue, and the next process taken from the front or from the head of the active queue is the next process that will be executed on the CPU. And you might think, well, if we take out processes from the active queue, and if they finished running, we let them join in the expired queue, then at some point the active queue is empty, right? Yes. If the active queue is empty, the expired queue is full, and then we just flip it. So the expired queue gets the active queue, and the active queue gets the expired queue. So they alternate. And this is how the scheduling works. Until today, I said in the beginning, there's a lot of research going on in scheduling algorithms in Linux. The scheduler is changed starting from kernel 6.6. Right now, I clear my shell. Right now, I'm running a kernel 6.4, and in the shell, what kernel do we have there? Yeah, let's close this terminal, create a new one. A little bigger. My Ubuntu virtual machine runs a kernel 6.2, so both my installs of Linux do not employ the newest kernel because the distribution did not add the newest 6.6 kernel into the distribution. But Linux kernel, if we search for it, you see kernel 6.6 is released already. So this is like changing the scheduler from 6.5 to 6.6. It's happening, but it's not rolled out to every distribution. So this is actually bleeding edge, what's happening right now. What does the new scheduler do better than the old scheduler? So the old scheduler is fine. We have in CPUs two like quality levels of cores. I don't know if you are aware, but newest Intel CPUs, I don't know if AMD CPUs have this as well. They have performance cores and they have power efficiency cores. So efficiency cores and performance cores. And the CFS scheduler does not take into consideration if a core is a efficiency core or a performance core. And the new scheduler optimizes towards having a lot of cores in the CPU as well as having different types of cores in the CPU. But if you are very interested, you can read some online articles about that. This will not be part of the lecture today. What we do today is we do a little assignment. So of course we train this. So there's an assignment scheduling. And this assignment also has a table that we know from the slides. So we have processes ABC, we have arrival times 0, 1, 2, 3, and we have these burst times. And the task is to develop a process schedule using round robin and use the provided sheet to draft your schedule. So I have attached a sheet that you can print out at home, and it has a timeline there. And the timeline, you can then enter your solution there. But as we are online, what I want you to do is use Draw.io. It's the online drawing application that I use for my diagrams, and everything, or every diagram that you see is drawn with Draw.io or diagrams.net. It's the same. And this is a drawing application that you can use in order to create your schedule, because you can just draw rectangles here. Where is there? No, here on the, if you take a look at the mouse cursor, and if you follow the mouse cursor here, you can toggle in the formatting options, where you can add some colors to the rectangles. And this way, you can also draw a nice schedule according to the lectures. And this is what I want you to do. So we do breakout rooms again, and one student should screen share, and together you develop a schedule according to this table with round robin, and one guy is the pilot, and this pilot then draws the schedule. You have 25 minutes for that, and afterwards we will take a look if your schedule was the correct one. Let me create the breakout rooms real quick. Create them. And we talk again after 25 minutes. Good luck and have fun. We have in the last task for today. So this is a scheduling table, and I will just show what the solution is, and you can compare accordingly. So this is round robin scheduling. What you can do at home in order to train your scheduling creation skills is do it with Shorter's process next. But this is my round robin schedule. And what's maybe the thing that I say to this is train this really at home, because especially for round robin scheduling and also for priority scheduling, you need to be aware of the list of currently runnable processes in order to decide which process you execute next. And for that, it is good if you trained it before the exam, such that you know how you write up the schedule and how you maintain the list. I did it this way, where I say, well, the list of runnable processes is shown in each, or shown column-wise for each time unit, such that I know if it's time frame 2 and A is currently running, besides A, the only process that's in the list of runnable processes is B. Or for example, if we take time 4 here, B is currently running, and the current list of runnable processes except for B is CAD, and I just take the top one and select this as new runnable process. Okay, yeah, and you do this. Well, this exercise is a little bit on the comprehensive side. In the exam, you can expect questions like this, but not in the extent that we do in the practice exercises. Does anyone have a question regarding this? No, then we can conclude for today. Thank you very much for attending the lecture, and talk to you next week. Bye bye.